Integrating and differentiating power series. So what will integrating differentiating power series do? So if we differentiate a power series, which is basically this power function here, we can do this very easily because it's just a polynomial power. We can use power rule. Now, what this will do is, if we integrate the power series, and differentiate, we can generate new functions. So what we can do is we can start with a known series, and we've got some known series now. The most basic one being x to the power n, which simplifies to the function 1 over 1 minus x. We can start with some known series, and we can manipulate them to generate new series. So we could do this with some basic substitution. We've done this previously where we have a negative x squared. We're going to substitute into this function here. So we're going to plug that into the x here and here. So we're going to generate a new function, 1 over 1 plus x squared, when we plug it into here. And we can also do this into the series, and we can plug that negative x squared into the series as well. So when we plug it in here, it looks like this here. Okay, well, what does that generate then? Well, what it will generate then is 1 over 1 plus x squared, which happens to be the derivative of arctan. And the expansion is just going to be negative x squared to the power n, and that just becomes negative x to the power 2n. So we get from 0 to infinity becomes 1, minus x squared plus x to the power 4. So it's an alternating series because of that negative. Well, that substitution generates this new function, which happens to be the derivative of arctan. So we started with a basic series, our basic function, our power series, substituted it in, we generated some new function in a new series, the function being 1 over 1 plus x squared. Now, since that's the derivative of arctan, if I integrate this new function here, so if I integrate that function that we had to start with, this one here, I'm going to generate the arctan function. So I know this from previous. Well, if I can integrate this arctan, or the derivative of arctan, I can also integrate the series that represents arctan. So that series is the same series I had before. So negative 1. So when I plug it into, so over here, if I plug it into our basic power series, I end up with that negative x squared to the power n. The negative generates that negative 1 here. That negative 1 here. And then the 2 to the x squared and n put together gives us the 2n in our exponent. And that series represents the series for, that's going to be our series for the 1 over 1 plus x. And what I want to do then is I want to integrate this expression. So notice I have my integral here, and I'm going to integrate that expression. Now, I've kind of factored out the parts that aren't going to get integrated, so the negative 1 is not going to get integrated. So really, I'm just going to integrate that x to the power 2n. So in integrating that, I'm going to generate the integral of the original power series will give me the function arctan. Okay, the integral of that expression gives me arctan, so the integral of that power series for the same expression should give me a power series for arctan. And in using the power rule, I get x to the 2n becomes x to the 2n plus 1. I divide by 2n plus 1 for the power rule. That's what I've highlighted yellow here. And that gives me this new function, negative 1 to the power n, and x to the 2n plus 1 over 2n plus 1. That series then represents a series for arctan. So when I expand it, I can use this series. So n equals 0 is I get x minus x cubed over 3 plus x5 over 5. And this series expansion could be used to calculate the arctan function. And the nice thing about this is, it is a polynomial series. I have infinite terms. So I can actually calculate arctan x to any degree of accuracy I want. And it's very important to understand that this allows us now to have a calculation that calculates the arctan of any ratio x to any degree of accuracy I need. Before, there was no calculation. We had to rely on our calculator, which either had it stored or in reality is our calculator is actually using this series to get us a very accurate value of the angle given any ratio. So this series then is our arctan function. So y equals arctan x is equivalent to the series n equals 0 to infinity of -1 to the power n, and then the power series part is 2n plus 1 all over 2n plus 1. This series expansion calculates arctan values for us, and not only that, it calculates arctan values to any degree of accuracy we need because of the fact of this infinite nature of this series. So the last point here is that the derivatives of integrals are continuous and differentiable within the radius of convergence of the original function. Well, what does that mean? Well, first of all, it's important to recognize that these are polynomial powers. So polynomials, the series are polynomials, and polynomials are smooth and continuous for all their quadratics, cubics, etc. Okay, since polynomials are smooth and continuous, their derivatives are also smooth and continuous. So that means that the domain of the original series or the original function, so if the domain of f of x is from a to b, the domain of the derivative or the integral must be a to b. So the radius must be the same. Okay, so the radius convergence stays the same. The endpoints where they converge may differ. So notice that it could be closed. If I had closed intervals in my original domain of a to b, they could be totally open, they could be half open, or they can remain closed intervals when we have our derivatives or integrals. The radius is guaranteed, the endpoints are not guaranteed.